So for our next lecture in steel design, our topic will be properties of steel section. I'm gonna be discussing all of these problems right here. The section properties or the cross-sectional properties of steel sections that we'll be using throughout the course. Okay, I can assure you that the computation of this will be easier to understand. So for our first sample problem, we have a basic section right here, a rectangular section with a width of 300 millimeters by 450 millimeters. First, we need to get the area denoted by A. Then the area of the rectangle is equal to base times height. And then as mentioned, we have base which is equal to 300 millimeters and the height which is equal to 450 millimeters. Okay, so therefore our area for our rectangular section, so 300 by 450 millimeters. So area for rectangle or for our section. For our lectures here, we have four sample problems. Will be progressive. This one is basic. We have intermediate, advanced, and our application for we're going to be using steel sections. So we have area for the rectangular section, 135,000 square millimeters. We're going to store it to A, or so you can store it and retrieve it later if we need to use the area or the value for the area of the section. Next, we need to get the location of the centroid or the location of the neutral axis. So centroid, it lies on the neutral axis. Its definition is it is the for rectangular plate, which is three dimensions, mass and weight. So centroid is the center of gravity in which the resultant for the weight is applied, or the concentration for weight is applied, or in which an opposite force could be applied to balance the weight of a certain object. So for a regular object, it's, it's going to be harder to figure out where the location of the centroid is. But for a regular shaped objects, for example, a square or rectangle, which is symmetrical, you can easily identify the location for the centroid. I hope you have an idea about this in your calculus class. So for our rectangular section, which is just a flat surface, okay, is defined as the centroid, which is the center of the area or the geometric center for the area. So you have distances along the y-axis or the vertical axis relative to the section. We also have measurement from the x-axis. So our reference point is the lower left point of our steel section. So our annotation right here will be y bottom or y bar bottom, which denotes that our location, our measurements from the bottom part of our section, which is also parallel to y, and the other measurement from the left of the leftmost part of our steel section, parallel to the x axis, horizontal. Next, for our computation for the location of the centroid, so total area multiplied to y bar bottom or y bar top is equal to the summation of individual areas A multiplied to Y bottom or top. So the total area is 135,000. Y bar bottom is unknown. So for a summation of areas, we could divide some complex areas with regular shapes if possible. Is needed the summation of the area and the individual distance from our reference line or reference axis, either the bottom or the topmost part of our steel section, 135,000 square millimeters. Multiply the y bar bottom is equal to 300 times 450 and multiply to the distance of 450 over 2. So our y bar bottom, or the location of our centroid as measured from the bottom part of our section, is 225 millimeters. For x bar left, same procedure, Vranius theorem. I hope you're aware with that. So your total x bar left, summation of individual A or area multiplied to individual distance from the left or the right of the local centroids. 135,000 x bar left multiplied to 300 times 450 multiplied 300 over 2. So x bar left is 150, or simply um our section is symmetrical, so therefore the centroid will be at the middle of the dimensions. Next, we have just need to adjust this. Next is just need to store 135,000 by y 300 450 and 450 over 2 shift, and then just shift store. For you need to store the value of y. It's simple, you have 235, but if it is a different problem, you have different answer, which could be a very long answer, very long number. You need to store the values for um, each intermediate answers, especially the ones that we need to use for subsequent computations. For example, the areas, the location of the centroid. So next is our centroidal moment of inertia. Okay, the centroidal moment of inertia. If you remember in your calculus class, okay, is the moment of the individual areas, or the second moment of the area about an axis. So you have our neutral axis, which are be denoted as the x-axis and the y-axis of the member. The neutral axis on the y and the x. So centroidal, it lies on the centroid of the section. Have centroidal moment of inertia, which is equal to the summation of the individual centroidal moment of inertia plus the areas, individual areas multiplied to d squared. So for the rectangle, which is easy, we have centroidal moment of inertia, which is equal to base times the cube of the height over the depth over 12. So I have the distance d, which is equal to the distance from the local centroid to the global centroid. Local centroid is defined as the centroid for the individual members, or a division in which we divide our section for easier computation. And then the global centroid is the location of the centroid of the whole member. We'll be using it on our complex problems on the next questions. Next, so we have base 300 and our height, which is 450, and cube over 12. I'm sure you sample problems like this in your other um, subjects. So we have 2, 2, 7, 8, 1, 2, 5, and then 3 zeros. So our unit will be millimeters to the fourth, or we can use our engineering notation. So we'll be using our engineering notation for the final answer of our problem with 4 decimal places. So we have 2.2781 times 10 raised to 9, millimeter raised to 4, and is store it to B, our calculator. So next, so our computation was the centroidal moment of inertia about the x-axis. So we moment the area, second moment of area about the x-axis. Next is the centroidal moment of inertia about the y-axis. Okay, so about the y-axis, hb cube over 12. So hb cube, so we have 450 multiplied to 300 cube over 12. So 450, 300 cube over 12. Centroidal moment of inertia about the y-axis is equal to 10125, and we have 5 zeros. 4, 5, millimeter to the fourth, or 1.0125 times 10 raised to 9, 0 to the fourth. Just in and out. Okay, next. Let's just highlight our answers right here. Some green inks. So area, which is 135,000. The y bar bottom or location of the centroid is measured from the bottom, and the left most part or fiber or steel section. Centroidal moment of inertia about the x-axis and about the y-axis. Okay, that will be our first part. For the next part, we'll continue our computations. See you then.